Alright, so ladies and gentlemen, we have reached the climax of the entire first semester, which was when we're doing derivatives, where do we go? Like, for example, if f of x is 3x to the fourth minus 5x to the third plus 6x minus 7, okay, and we do the first derivative, f prime of x, pretty simple stuff. We all know that it's going to be 12x to the third minus 15x squared plus 6, and obviously nothing after that because we got constants. Okay, and even if we did the second derivative of it, it would be 36x squared minus 30x. Okay. All right, so we worked our way down. So this entire semester we have worked our way going down in derivatives. Now, what we're going to do is start to go backwards. We're going to learn some pretty cool stuff by doing it. And what we're going to do is, this is going to be called derivatives, and this is going to be called integrals, or antiderivatives. Okay. All right, so when we're going backwards, let's say we just start with a simple function. Let's say x to the fourth plus 3x squared minus 9. Something that looks like this. Okay, and let's say that this equals f of x. Okay, now let's say this before. We can ask ourselves now, what did we do a derivative to get to this function? Okay, and so that's some really interesting stuff that we just work right here. Okay, now if you notice, the variable or the coefficient in front of x is 1. Okay, so we had to multiply something by 5 to get 1 there, and that number was 1/5. So this is going to be 1/5 x to the 5th. Okay, so that's pretty cool that we can actually go backwards that way. Now we also know that we had to multiply something by 3, right, to get the 3 right there. All right, and 3 times 3 is obviously not that, but 3 times, I don't know, maybe, let me see, 3 times, no, it probably is just 1. So it'd be 1 x to the third. Okay, and then obviously we would have to bring in the 9x. It would be minus 9x, because just multiplying that by the 1 times 9, and then all that stuff. Now here's the thing, what do we put after? Because there had to be some kind of constant. In other words, guys, we don't know what there was there before. Okay, it could have been 15, could have been -3, could have been pi. Who knows? You know, whatever it was, we don't know. So what we're going to do is, whenever we do the antiderivative, we're going to put a plus c, just to represent a constant that existed, but we just don't know what it was there before. Okay? All right, so whenever you do an antiderivative or an integral, you're always going to be putting a plus c at the end. Okay? Something as simple as that. All right, so the basic rules are this. Okay, so where we're going to go from here, you guys, is we're going to go right up to here and go the rule, which is the integral of f of x dx, and this is important, we just talked about differentials and everything, is going to be capital F of x plus c. It always is going to be that way. So this is going to be the integral that we anti-derived from before. Okay, and the dx is important because the dx is almost like the ending spot for where we stop doing an integral. Okay, so for example, if we were to do the integral of, let's say, 3x squared minus, no, let's not go 3x squared. Let's go 5x to the third plus 3x minus 6. Okay, and then we write dx after that. Okay, so we're going to do the derivative of everything in here. Okay, so this is going to turn into 5/4 x to the fourth. Okay, plus 3/2 x squared minus 6x plus c is what I would do right there with that one. Okay, we'll talk more about everything that goes on with trying to get the integrals there. Now, however, if I did that same exact problem, but I put the dx next to the 3, I would just do an integral, or I would just do the integral of the first two terms. So it would be 5/4 x to the fourth plus 3/2 x squared plus c minus 6. Okay? All right. And so that would actually be set up that way. So in fact, what I did was I noticed that only the first two terms are being integrated, so I just dealt with those two plus the c at the end, and I just left this alone as a constant. So wherever dx ends is where you stop doing your integration and everything. Okay, now there are some simple rules for it. Some simple rules for it. If you have a constant out front, bring it out to the front, or if you have a constant in front, you can go ahead and bring it out here. If you have a negative, make sure you move it out front, because you really only want to be dealing with negative or positive integrals. Okay, if you are adding or subtracting two functions and then you're integrating them both, you can also separate both and do integrals of all of them. So technically I've been doing integrals here the entire time. That's why, you know, I just treat these all separately up here. Okay, now division and multiplication, you cannot multiply and divide integrals and just have them be as simple as that. We're going to learn some rules later. But adding, subtracting, factoring out a negative or a constant while integrating is very important. Okay, now if you notice, there's some pretty important things here too, is that I've been working with this. Let's say we've got, okay, let's say we're integrating 2x dx, and then over here we've got, oops, let's go ahead and get, sorry, I have to type in both, 2t dx. Okay, now if you notice, the only difference is the variables here. Okay, so when I do the integration here, it's going to be x squared plus c, and I'm done. Okay, so that one's pretty simple. But when I do this one right here, okay, it's going to be 2tx plus c, because I can't integrate with respect to x when I have a different variable there. So it's almost like implicit differentiation all over again. Okay? All right, and that is pretty much it. Just remember the rules we'll learn later for multiplication and division. But right now, antiderivatives and indefinite integration are pretty darn cool. Okay? All right, that is it for today, and I will talk to you guys later. Have a wonderful day. Bye.